Okay, so I restarted the recording. We still got a couple of minutes before we get started again, but yeah, reading your responses, a lot of interesting uh, things going on there. One of the things I always like to emphasize, whether mentoring, younger engineers or teaching a capstone course or something like that, is that we are always constrained in engineering endeavors, right? So, and it's really important that we identify what are we trying to do, right? Are we trying to solve some sort of problem, right? So it's helpful to identify the problem, and through that, then we can identify our objectives, right? What do we really want to accomplish, so that maybe we write some sort of optimization type function that we're going to optimize our design for, right? What are our objectives? And rarely is it just one objective. There might be a main one, but there might be a few others. And but then there's also constraints, right? And we're always constrained. We always have some sort of fixed budget. We always have some sort of schedule that we're dealing with, right? We want to deliver by a certain time, or bring our product to market within a certain time before investors get shaky and that type of thing. There's also, those of you who've been working in the field probably have run across this term, the swap, right? So, and sometimes we call it swap C also, and that's a size, weight, and power, almost always factoring into our constraints. C stands for cost, and so then yeah, and challenges. I think you guys are doing a great job of highlighting those challenges, right? So, but that's kind of one of those soft skills that I think is very important in engineering. Also, is the ability to look at a project and as I say, try to identify your objectives, identify your constraints, but then kind of figure out where your challenge is at, because that's where you need to put your resources, right? And that may be where you need to go and do a feasibility study, right? And make sure that you do have a pathway to overcoming those challenges before you spent 3 years and $40 million trying to develop something. Make sure it's feasible first, right? And so part of that is looking at your challenges and being able to then properly budget, and both in time and cost and resources that it's going to take to get there. All right, so very good. I'll look at the rest, but yeah, thanks for those answers there. Let me go back. Hopefully, we've got everyone back, and we'll dive back in here. And so, considerations, right? So, as I was kind of rambling on there, engineering is typically about optimizing a solution for certain considerations or objectives while dealing with a set of constraints, right? So, we've got the basic mission, but we also want to, consider safety, comfort if we have passengers involved, energy efficiency, speed, might be plenty of others. Um, so this is from the textbook. This is the author's vehicle implementation. I emphasize single vehicle here because, yeah, there's, as we mentioned a little bit earlier, there's an opportunity to have vehicles collaborate with each other. But as we kind of saw right before the break, we've got some of these basic functions or operations going on in an autonomy system, right? So we're sensing the environment, and we might use GPS or IMU, oh, I always get these INS and IMUs mixed up, but you're using inertial measurement to help determine where you're at, right? So you're measuring movement in terms of acceleration and velocity over time. And if you know your starting point, then you can kind of keep your location updated by tracking which direction you're going for how long and for how fast, right? LiDAR is a light emitting detection radar type system using lasers instead of radio waves, right? Cameras. We could add a few more sensors in here. Millimeter wave radars are often used as our ultrasonic sensors. So, but regardless, you've got a set of sensors operating over here, and they're operating on within some sort of operating system, typically Linux or a real-time operating system, or RTOS, and then on top of a hardware platform, right? You got to run it on some sort of processors and chips and with memory and that type of thing, right? So then you have your perception area, and now we're trying to actually take all these inputs and determine our localization, recognize objects around us, and then be able to track those objects as they move and as we move. This is non-trivial to begin with, but gets particularly difficult when we've got, let's say, a lot of noise or interference in our system, and sometimes we lose track of an object and we have to pick it back up again. Or that we might have two objects that we're tracking and they cross each other's path, right? And now we need to be able to recognize that, just for example, the object that had been on the right side is now on the left, and the object that was on the left side is now on the right. And they're at some point they might have converged to a point. There may have been a near miss there, let's say, right? And or at least from our perspective. And so tracking is not always a easy thing to do, right? Then we have our decision modules, and we need to do kind of our high level path planning. How do we get from A to B, and what are the big steps and where are the little steps, right? And then how do we translate that into action? What about outside of all this, all this pipeline going on here, that we suddenly detect an obstacle right in front of us, and we need to kind of abandon our other plans and just focus on avoiding that obstacle, right? So there's kind of a path through this that is focused on the big picture, but then there needs to be kind of a very low latency, high reliability path that says, hey, no matter what else we're doing, we don't run into anything, right? So we make sure that we're safe at all times, right? So all this is running on a vehicle. All this is running in real time, right? And so there's going to be deadlines associated with making these perceptions and making these decisions and that type of thing. We can't get behind. We've got to do those in timeframes that are make sense for how fast we're traveling and what's going on around us and how fast things are happening. But then we have these other things that might be happening in a more batch type situation in the cloud. Now, for a connected vehicle, we may want to reach back to the cloud to get kind of real-time traffic information. But then there's also kind of these batch type of things, right? So we're going to collect a lot of data from all these vehicles driving around. We're going to need to store that. We're going to use that data, maybe some other data, to train some models, to build up some maps. We might get data from exterior sources, but we might also use what the vehicle is seeing in real time and building up maps according to what those vehicles are actually seeing out there. We might be running lots of simulations to try to enhance our model training and testing and validation. And all this is done on a cloud type of environment. Oh, I guess I had handy little rectangles here to talk about as I went through there. I forgot about. But then overriding all this, yeah, we've got this safety that we've got to be concerned about at any time. So, at all times. All right, so we did talk a little bit earlier about now, what if we can communicate with other vehicles? What if we can communicate with some infrastructure? So, yeah, we might have a vehicle-to-vehicle type communication system going on here. 5G was designed with some of this use case in mind. And 6G is likewise being designed to kind of facilitate this vehicle to vehicle and vehicle to infrastructure type of communication going on. So these vehicles may form a bit of a convoy, and so there's if you're a traffic engineer, then you might study what is the optimal following distance. Tailgating, it turns out, is one of the biggest things that slows down and causes kind of traffic bubbles, so to speak, where they're not due to any sort of accident or construction. They just happen, right? And it's because there was one car that was tailgating, and then that kind of cascades when someone's brakes go on and all, right? So if you have great communications ability, then you can form these optimal convoys and really streamline traffic top thing. But that's kind of a long-term situation. You need a high percentage of vehicles participating for that to actually make sense. But you can have a car in front warn cars behind that, hey, I'm starting to slow down, or there's some issues up here that I perceive that you ought to know about, right? So that might be some construction going on. We might need to perceive these, and maybe there's some collaborative sensing that's going on here, right? So we might be at an intersection and could observe that, hey, this is a red light, and kind of pass that on. Some highways, you'll see signs that will warn you of be prepared to stop ahead. So that type of communications can go on. All right, let's look at localization. Now, we'll spend a couple of whole lectures on this, but just want to introduce it right now. So we need to understand the ego vehicles, location and orientation, also known as the pose. Pose is more of a robotics term, but it's used in autonomous vehicles also. We need to project where it will be next, right? So we need to know the speed and bearing, or the velocity is a vector. So if we know where we are now and we know our velocity, and we can project that over a time interval and have a pretty good guess at where we're going to be. And that's important to understand how we fit in the environment, right? So um, uh, you know, no sensor is perfect. GPS is pretty amazing at what is enabled for us, but it's still not perfect, right? So um, GPS might be in error when we might have a reflection that bounces off a building in what are known as urban canyons. So you think you're driving, think of driving in Manhattan, and you've got all these buildings above you, and that satellite signal is trying to get down to you and in between all those buildings, and it's actually bouncing off of them. It might be bouncing off a mountain or something like that, right? And that's going to cause some errors in that localization. And so, let's see if I can hide that. And so we might also have this IMU over here, and it's got a combination of accelerometer and gyroscopes and possibly electronic compass inside it, right? And so the gyroscope will kind of help us measure rotational type things in 3 axes. Accelerometer is going to do same thing, but for linear motion in 3 axes. And the electronic compass will make it easy for us to know which direction we're actually pointing. And also, we can combine this information and this famous Kalman filter approach, where we have a prediction from a model, and then we have this update. And so this operates in a circular manner also. So the problem with IMUs is that even though they give you super fast update rates, far faster than GPS can, and they're generally always going to be available. The data is always going to be available, but they drift really badly, right? So, if you've got a giant one that might be on a submarine, let's say, that thing's going to have very low drift. And some of y'all I've had prior students that are working on gyroscopes for that type of application, right? And so those things may have very low drift, but one of those is about the size of your car. So you're dealing with now microelectronic versions of these, and so or micromechanical versions of these. And so they have a lot of drift, so they need to be updated. So this Kalman filter will take these inputs and predict what the next pose is, right? And considering that there's some movement, and it will say, okay, now in this next instance, I think we're going to be here and pointing in this direction, right? And now we occasionally get an update from the GPS, and we will fix any errors and update that pose, and then we predict it, and then we update and we predict. So this is kind of taking advantage of the best features of IMU. and it best features a GPS and hopefully negating some of the challenges associated with them. So we'll look at that in more detail, kind of taking this and going to the next level or implementing something like this with some real sensors might be a fun project for someone. GPS, I think everyone's familiar with GPS at this point. It's an example of a GNSS system, a global navigation satellite system. Other systems include the Galileo, GLONASS, Beidou, I think is how it's pronounced, QZSS, and Airness from India. These provide either global or regional coverage from space. They're very accurate, but obviously must see the sky. And as it turns out, the signals are quite weak, and they're susceptible to jamming and spoofing, and a lot of different ways of trying to handle that, trying to improve the accuracy, trying to improve robustness to spoofing and jamming. But these things are real. There are real cases of both jamming and actually spoofing in some conflict areas where ships are suddenly seeing signals that are indicating that they're very different from where they're actually at. So GPS, as it turns out, provides time, very, very accurate time. It's based upon atomic clocks and stuff, as we'll look at in a little bit more in detail, but it also provides latitude, longitude, and altitude. So it provides, some people call it a 4D fix, but it's a fix in three dimensions plus very accurate time. With subsequent measurements, or just with trying to measure Doppler directly, we can provide the speed and heading of the vehicle also, right? So, I mean, just at a macro level, you can look at your latitude and longitude over a number of time increments and kind of build up your speed and heading from that. Or, like I say, look at the Doppler signal itself. So, but it can take a very long time to obtain an initial fix. We've come up with lots of techniques that mostly mitigates that, but that's, still has to be a bit of a concern. Kind of the worst case scenario, it can take you minutes, like up to 12 minutes to achieve an initial fix. You're rarely ever in that situation, but that could be a worst case scenario. And the update is relatively slow. So, consumer level GPS systems, we typically emit one fix per second. Nowadays, you can get ones that are 10 hertz. So one every 100 milliseconds outputting a fix. So the IMS, the inertial measurement unit, as I mentioned, so it's got a magnetometer, magnetometer, electronic compass, easier to say, so I say that, accelerometer, and a gyro. Here are update rates. Instead of being ones per second or one every or 10 per second, now it's 500 hertz, right? So much more faster. But as I mentioned earlier, it drifts rapidly because you're really doing integration, right? So your errors are going to accumulate over time. Your LiDAR, laser-based ranging system, typically used with a particle filter, which don't expect you to know yet, but we will talk about that. But basically, it's reconciling its reflection data from this LiDAR instrument with an a priori known map to determine location. So basically, this laser spins around and records the distance to reflections from its center point, right? from its transmitter and receiver. And then we run this through this thing called particle filter, where we start off with our map, and we don't know where we're at on that map, so we sprinkle it randomly with a bunch of we'll call them particles, right? So location candidates is maybe a better way of saying it, right? So you don't know where you're at in this area, so let's randomly generate maybe 10,000 different locations. And now let's begin to compare what we're seeing from reflectivity with what we think we should see if we were at a particular particle and with that map data, right? So, and then we do that for all the particles, and the ones that match the best with what we expect to see compared to what we are actually seeing in terms of reflections at a certain bearing and a certain distance, then we save those and we get rid of the others. And then we resample again. And but now when we kind of regenerate another 1,000 or 10,000 samples, we do it probabilistically, weighting those areas that seem to match the best, right? And this will converge typically pretty quickly. Depends on how complex the environment it is. Actually, the more rich or complex the environment, then the more uniquely the more of a unique match you're going to have, so you'll actually converge faster. It's when you have plain boring environments where everything looks the same that it has a hard time converging. So so LiDAR in its basic implementation is used as a localization device. But we also have cameras. Of course, as humans, we're very, very reliant on our vision capabilities, right? So as predators, we're like a lot of predators. We have eyes facing forward, but spaced apart, right? So we have the stereo or binocular vision, and with that we can focus very narrowly if we want to, and we can discern depth in doing so. We've got a little bit of peripheral vision, so we know what's going on around us, but kind of our claim to fame is very high resolution vision in the direction that we're looking, right? So so Tesla has kind of concluded that if it works for humans, it'll probably work for autonomous systems. So they have over time gone to a camera-only system. We might qualify that a little bit later, but they have instead of just two cameras, they've got cameras spread around their cars. But generally, there's typically two cameras that are pointing in any given direction, and getting some stereo binocular vision to provide that depth. It's not necessary that you actually have two cameras to do this. You can do it with one. So there, I'm not intimating that there's pairs of cameras everywhere on a Tesla system, because we can do disparity. And so in the kind of prior art, we would do this in computer vision using a toolkit like OpenCV, where we get one frame, and then we would move the camera. That's easy on a car because we're moving, right? And now we grab another frame, and then we compare the two. And if you look at these two images, we're doing some disparity mapping here, in that things that are far away will map to very similar pixels in these pair of images, right? But things that are close are going to be mapping to very different sets of pixels, right? So do the old experiment of here, I'll just um, do this real quick, right? So put your finger up close to your face and close each eye subsequently, right? So look at it with one eye, look at it with the other eye, and that finger moves back and forth. It appears to move, right? Even though you're holding it steady. But put it way out and do the same thing, and it barely moves, right? So there's no math to that. Sorry, we could come up with equations, but I think that's just super easy way of understanding disparity mapping. So so yeah, you can do it kind of conventionally with stereo or binocular vision, or you can do this disparity mapping with subsequent frame processing, and so you can even do it with one camera, as I'm saying. And if we then kind of process that whole thing over frame to frame, now we can discern relative motion relative to us, right? So this would be a visual odometry pipeline. So we've got this triangulation, feature detection. So, again, you got to remember that when a computer looks at one of these images, all it's getting is RGB pixel values for all these different pixels here, right? And when we look at that image, boy, we are subconsciously creating all sorts of features out of this, edges and lines and circles and that type of thing, right? So we need to actually implement those functions in this pipeline, right? And finding features and matching those up, and then like matching this feature from this image to that image, and then creating a motion estimation where we use this previous disparity map from the previous set of processing, and then we can update our vehicle position from that. So all right, then we've got ultrasonic sensors. These are simple enough. You can plug these into an Arduino, right? And they're kind of a classic peripheral for the hobbyist level Arduino type stuff. And they can provide that close-in ranging information using echolocation. Now we're using sound. Sound travels at a much slower velocity than EM fields do, of course, EM waves, but primarily used for parking assistance, right? So it's really hard to get a very narrow focused beam with these sensors unless you're using an array of them, and that gets expensive. So similarly, now we can use millimeter wave radars around 60 to 70 gigahertz. Now the wavelength's really small, so we can therefore discern small features with that, and we can also use a wide bandwidth. So that also helps us be able to discern small features, closely spaced small features, right? We can discriminate them. Simple systems used to warn of obstacles at a distance farther than ultrasonics, right? So we can get out to 100 meters or so versus just a few meters with ultrasonics, right? So these are commonly used in cruise control systems, which will maintain a set distance to the vehicle ahead of you, and some relatively newer systems and this is still to a degree aspirational. I mean, these systems exist that use antenna arrays. These are still integrated on a chip or module level. So the real basically tiny patch antennas, and typically use an array for transmit, an array for receive, and what's called a MIMO, or multiple input, multiple output type system. And hopefully we'll have a chance to dive into some depth on these. But that allows us to get a little bit more imaging capability, be able to focus our beams, basically. I'll say that with a little bit of hand waving because it's not quite a beam forming type of system, but allows us to be able to discriminate things at a distance. And so our small wavelength kind of enhances resolutions with our limited antenna aperture sizes. So that's interesting. Elon Musk, Tesla is kind of famously or infamously, kind of downplayed radar in favor of vision type systems, and but he's kind of stronger against LiDAR. But he's got a lot of comments about millimeter wave radar in terms of is it good enough to play any role in autonomous vehicles, and so that's informed a lot of Tesla's engineering development. But as it turns out, they still on their latest embedded hardware solution, they do have a port for a radar chip to plug into it. So did talk about a little bit of sensor fusion. No sensor is perfect. So basically, we're going to fuse the data together to get the best of all. We'll talk a little bit more about this later, so I'll kind of skim over that a little bit. As I've mentioned, key part of this optimal approach is to have these high resolution, high definition maps continually being built and rebuilt and deployed. And this is not necessarily the only way of doing it. And you can be totally reactive and to any given situation and not rely on these high definition maps. But this is the textbook approach, right? So, and when we say high resolution, we mean down to that lane level, and knowing that a particular lane might be a left-only turn lane, another one might be a through lane, another one might be a through lane also, but if you back up, it might split off onto a ramp and all that, right? So we need to know all these different lane segments. So you'd have to continuously gather and merge and then distribute data out along with these new maps. So we're starting with this raw data. It might come from a LiDAR system, which then gets organized into what we call a point cloud. So you might have a region, and now you've got all these different pixel level responses that are forming this thing we call a point cloud. We need to register that in real world coordinates. So the vehicle, it might be relative to the vehicle, but that's if we're going to merge that into a map, we've got to be able to align that perfectly with or close to perfectly with the real world. So the localization of our vehicle may not be quite good enough. We might need to like merge this with a priori known information. So we kind of register new data on top of old data, right? So now then we can kind of create this 2D reflectance map and then label it. And, somehow we get to these type of things, right? This is our low resolution map over here on the left, and our high resolution map here in the middle. And then we push that back out to the vehicles. We'll get to this hopefully at the towards the very end of the course. Yeah, so alternative approach, right? So again, apologize for keep bringing up Tesla, but they do things differently, and they talk about it to an extent. We don't know everything they do, but they do talk about it. So it's good to pay attention to them. So they're taking a different approach. As I noted earlier, humans primarily drive using vision. We feel turns, and in our bodies we kind of sense g forces, and we hear things and that type of thing. But I think we all can accept that we're we're dominantly relying on vision, right? So autonomous vehicles can achieve human level performance or perhaps superior using cameras. Well, that's assuming that our camera technology is approaching that of our retinas or better. That includes not just resolution and practical resolution, right? So it's not just number of pixels, but our lenses good enough to render the photons onto those pixels correctly. And do we have good dynamic range out of each of our RGB sensors in each of those pixel locations, right? And stuff, right? So there's a lot to that. But the other certain advantage we can do is most humans that I know of are limited to 2 eyes at most, right? And but we're not limited to that on an autonomous vehicle, so we can have multiple cameras and all feeding a common model. So now we have 360 degrees of awareness all around us. So cameras have far higher resolution than these other sensors. Well, to an extent, LiDAR has very good resolution, but still it's kind of rotating. And so the farther out that your laser is going before it gets reflected, that's translating to a larger kind of conic section and therefore lower resolution, right? But yeah, Tesla's kind of point of view here is that the cameras are so much better than the others that there's really not much sense into trying to do the sensor fusion process, and that it doesn't even make sense to use them. So there's a couple of videos, one from CVPR conference in 2021, and then another one from this year, just a month or so ago, a few months ago, talking about that. Those are linked in Moodle, so I think they're very good from the top AI directors at Tesla. So I encourage you to take a look at those, and they'll say it better than I can. All right, so yeah, so if we have many cameras, then we have up to 360 degree vision, and of course that's in a planar. We can also go up and down. One of the complaints that Elon Musk has brought up with radars, and perhaps technology eventually evolves to solve this, is that existing radars don't have very good elevation discrimination, right? So their beam that they're putting out is kind of wide in the vertical direction, and can get pretty good resolution in the azimuth or kind of rotational two-dimensional direction, but that does cause some problems with discriminating between, let's say, an overpass and other vehicles moving ahead of you, right? So one of the if anyone has driven or ridden in a Tesla long enough on this auto pilot mode, you will have experienced the sudden braking because it sees an overpass ahead of us, and it can't tell that that's a overpass or a stopped vehicle in the traffic lane. So that's been blamed on reliance on radar, and so the newer systems have kind of dropped the radar, and they don't even put it in their vehicles anymore. Maybe there's some qualifications there, but so now with vision reliance, now that problem is seeming to go away. And I can attest that I don't experience that problem as much anymore with all the recent software updates. All right, so with multiple cameras covering the same area from different viewpoints, the machine learning model can learn to perceive depth, right? Whether it does it using this, where'd it go? Disparity map type of all this mathematics, or whether it just learns it, right? It's learning it, right? So it is learning, and it's one of the challenges in machine learning models is we don't always know how they're learning something, right? But it does this approach, as all machine learning systems require this. It's just when you go to a purely vision-based system, it gets all dramatically much more complicated because it requires a large model, high quality, large data set, and massive compute capabilities, right? So we need a large model because we're starting off with many millions of pixels of data, right? Because again, it's just take one camera chip, right? And it's got a lot of pixels, right? Multiple gigapixel type resolution. But now you have multiple cameras that you're trying to all stitch together into a 360-degree scene. So it starts off very large, and all that we're trying to do with these models, there needs to be a lot of complexity in the model as we go through it. And if you have a large model, you need a correspondingly large data set, and it needs to be fairly high quality. In kind of the early days of deep learning, we kind of, and the big data kind of revolution in general, we said, well, more data is better than than anything, right? We just want lots and lots of data. But now we're kind of evolving back to, yeah, we need lots of data, but the better quality that data is, the better our models will train, right? So but then to do all this training, we need massive compute capabilities. So how does Tesla get these data sets? I better keep track of time here. Tesla collects massive amounts of data from its large fleet driven by customers, right? So our cars are connected, and so they're constantly collecting data, and they can correlate that what the sensors are seeing with what the driver, how the driver reacts, right? And so the driver may stomp on the brakes, and they can correlate that to what would the driver have seen. Let's see, we can maybe show you a little bit of this talk. This is one of the talks. Okay, so this is from 2021. But the point is here to collect this rich data set that encompasses all these edge cases, not just the nominal behavior, but all sorts of edge cases. They've kind of analyzed all the raw data that they're getting and have developed and are maintaining 221 triggers. Now, again, it's 2 years old, dated, so I don't know how accurate this is now, right? But just to look at a couple of these, right? So, well, yeah, did the radar match what the vision was doing? All right, so bounding box jitter. Well, we haven't really talked about bounding boxes yet, but that's part of the machine learning model that says, okay, there's a car up there, or an object, let me draw the exterior rectangle that encompasses that whole object, and that's called a bounding box. And then, that is done to a certain level of accuracy, right? And there's ways we can measure it. We have metrics to measure that. And so if that bounding box is jittering around a lot, then they're going to flag that and pay particular attention, gather that data, use that in your training set, right? How about a detection in the main camera, but not the narrow camera, right? Or the driver didn't brake, but the tracker and the autonomous system thinks that the closest in-path vehicle is rapidly decelerating, right? So it's the tracker's detecting something, but the driver didn't. Maybe ran into it, but maybe the tracker is not seeing what the driver's seeing, right? So all sorts of these. So you might look through these and see how they make sense to you when you watch this linked video there. All right, so they have developed all these triggers, and these correlate to these edge cases that they want to make sure that are getting incorporated into the training data set. So here's where I can, in one run-on sentence, I'm going to tell you how machine learning models work, right? So you could, take a whole graduate level course on this, right? And I'm going to try to explain it in one sentence. But machine learning models are trained by feeding the network or that model inputs with corresponding correct outputs, right? What someone is labeled as to being, okay, if you get these inputs, this is what the output should be. And then you adjust the network or all the parameters in the network to produce those outputs in a process called backpropagation. Okay, and there's lots of subtleties in actually how you adjust all these parameters, and it's gets particularly difficult as we go to very deep networks with many different layers on them. And so we'll get into that in the middle part of this course. But that's just a super high level idea on what's going on. So what you need is this network, but then it has all these parameters. They may have 1 billion parameters that you need to adjust. Well, if you have 1 billion parameters to adjust, or even just 1 million, you need massive amounts of data to be able to train those. And in doing so, what we want to do is we want to make sure that we're learning these generalized concepts and we're not just memorizing, right? It's a important but perhaps subtle distinction. If we don't have enough data, then the best we can do is kind of memorize. And if we get the same data, we'll produce the same results. But if we get different data than we've ever seen before, we might not extrapolate or interpolate very well, and we might end up with some really weird results because we're memorizing rather than generally learning. So Don't worry about that too much at this point. Just it's really implying that we need large, massive amounts of data. So, as I mentioned before, assigning the correct outputs with the various inputs is called labeling. Labeling is typically the costliest portion of model development. Auto labeling incrementally builds a model to label data items in a data set. Okay, so it progressively automates the process under human supervision. There's a nice open source um, tool called Label Studio. They also have an enterprise version. My old company also kind of did a fork of this and did some, big improvements and stuff. So there's lots of interesting things to do here, and you can follow this. But we won't for the sake of time. But the idea is that you provided a few samples out of your data set, and then you manually label those, right? And then the system looks at that and it tries to build a provisional model to do that same thing. And then you can run it on some more data, and then you can kind of see how it did with that very initial provisional model, and you tweak it and you correct what it tried to predict, and then it will refine its model. And you do that for a few iterations, and it quickly converges and can then basically automate that whole process. Now, you still probably want a human to do some QA checks on it and that type of thing, but very important aspect of the overall kind of end-to-end machine learning model development ecosystem. So using these triggers, their version of auto labeling, I'm just giving you an open source example. They have their own technique that I'm not privy to, but using that set of triggers they came up with, those 200 some odd, they're auto labeling, and its large connected fleet. Tesla builds terabytes worth of labeled data with which to train their models. And then they additionally use generative techniques to synthesize some data, right? So this is generative techniques. I think we've all been hearing about this over the last, maybe a couple of years with Stable Diffusion and DALL-E, and over the last 6-9 months with Chat GPT and all. Everyone's heard about these things now, right? So these type of techniques to actually generate in a disciplined way things like lanes and whatnot to actually enhance its data sets. So again, those pair of videos, I think, talk about this in a little bit more detail. So I did snip these next couple of diagrams right from those videos, and won't go through all of this quite yet, but we start with raw images from all the various different cameras. There's then some featurizing, right? So how do you take all those RGB pixel values, those millions, billions, whatever, all of those, and in a particular frame, slice of time, and then make sense of those, right, as features. We're not even like recognizing objects yet, but we're trying to figure out, is there a line there? Is there an edge? Is there a curve? That type of thing, right? So and then one of the things that's kind of accelerated machine learning development lately is this idea of attention and transformers. there's a lot there that we probably won't have time to get to, but that's been one of the things that's really enabled a lot of these super powerful type systems. And then we've got to kind of sort things out in time, right? So now we might be using some sort of recurrent neural network, something that's got a little bit of feedback to it, a little bit of delay, and a little bit of feedback, right? So we can start to organize some of this stuff into time. And so we have some spatial aspects, and we have some temporal aspects, right? So, and then, yeah, various type of outputs. Here's a look at their object prediction and properties. So you've got these different cameras coming into these RegNet type of deep. These are all deep neural networks themselves, going through this transformer type of architecture, and yeah, doing some further processing. I think the one of the things that take away from some of these things is that there's a lot of like input processing, and then they try to do a lot in common with a lot of this kind of feature detection and feature detection of things. And then they kind of split out into different various functions, right? So now you have a branch here that's responsible for doing future trajectory, a surface mesh, pedestrian pose, ... right? So now this gets stamped out in this, but there's a lot in here that's all in common, and that helps them scale the system up. All right, so then data center, the training, just the ability to access compute is another key aspect of developing these autonomous vehicles. Graphics processor units, GPUs, facilitate massive parallel programming. Years ago, I taught a graduate course on parallel programming. Perhaps I'll get to teach that again in this spring. We'll see. But these things have now hundreds of cores, maybe even thousands. But the important thing is that it's very low cost to launch new threads on these GPUs. So kind of outside scope of this course, but they are essential in scaling up for these large networks with this massive amounts of data, in order to be able to do as much of this in parallel as possible. Otherwise, it would just take forever. So, excuse me. Tesla has been talking about their Dojo supercomputer, and now it's really just coming to life now. It will still be growing and evolving over time as they get more GPUs to plug into this thing, but it's massive. It ends up being one of the most powerful supercomputers in the world. And considering that most of the top supercomputers are used for things like simulating nuclear weapons. So the DOE, Department of Energy in the US, has been at the forefront of superconductor work, and they're the ones that are responsible for nuclear weapon effects and design and that type of thing, right? So since we don't test much anymore, then those things, then that's been dominated by supercomputers running these massive simulations, right? So that's just to compare what now is the level of problem that we're dealing with, is that this Dojo supercomputer is now rivaling and surpassing those computers. You can follow this link. It's just a kind of a popular media type of analysis, but it'll give you a little bit more information there. So, but think a little bit about this, and that's another thing that I want to pull that I'd like you to actually hang on. Let me just give you a short one. So let me drop that in the chat here, and go ahead and save that so that you can just kind of write that up for fun later. It's just asking you for a paragraph with the idea of exploring. You know, it takes a huge company with massive scale of all these cars in its fleet collecting all this massive amounts of data and this incredible vertical integration to have their own data center to be able to train these large models on. And think about that, the competitive implications of that, right? So, you know, and especially considering that kind of the other big players in this are also big players, right? So Waymo is owned by Alphabet, which is the Google company, of course, and Cruise is owned by General Motors, I think. And so these are some of the largest companies in the world. And you know, can others play in this market? Just something to think about, right? So, all right, a few more minutes here. So now we can kind of switch into kind of basic functions again. This is a little bit repetitive. We talked about these before with a little bit of subtle addition here in lane keeping behavior. We might be concerned about, well, we are concerned about both longitudinal, right? How are we with respect to the car in front of us and a car behind us, right? In that longitudinal direction. And also in a transverse direction where we well centered within that lane. One of the annoyances of driving a Tesla on autopilot is on the highway is when there's an exit ramp and the stripe, depending upon the lane striping, it will, for a short period of time, look like the right-hand lane and the exit lane are one big lane. And the car, even though it's programmed to keep going straight, will try to center itself within that apparently large single lane that is really the through lane and the exit lane. And so it doesn't commit to exiting, but it's seemingly not committing to going straight ahead. It looks like it's going to run you right into the sign that's at the divider, right? And then it corrects, but it's quite unnerving. And so that's an example of not really very good transverse lane keeping behavior there. So, all right. So use cases. We talked a little bit about these, and these are just some. That's all. Interstate pilot using a driver for extended availability. Maybe you know, when you're a commercial driver, you have certain rest times that are mandated and that type of thing. Maybe we can evolve to a ability to extend that and keep the truck or the commercial vehicle on the road instead of in the parking area. Autonomous valet parking, full automation for using driver for extended availability or vehicle on demand, right? So some of these are not unmanned, some of these are manned, but still some interesting use cases, right? We've talked about some considerations with, in that little poll we did. Safety, comfort, energy efficiency, speed. Nowadays, if you do a map using Google Maps that I'm familiar with, it will typically give you a route that is flagged for energy efficiency. It may not be the quickest or the shortest. It might be the most energy efficient, and also some of the challenges. So ambient conditions, lighting, weather. One of the challenges with a full vision oriented system is that there are times when I'm driving into the sun at dawn or into the sun at sunset, and it blinds the camera. And the system refuses to go into autopilot mode because of that. It won't even go into like a cruise control mode because it's relying on the camera to do the cruise control, and it's basically blinded, it's saturated, and it's lost its dynamic range. Certain rain conditions or icing conditions will do the same thing, right? So it will basically blind the cameras. Yeah, there's ways around that. You could have some mechanism to wipe the camera lenses. You could swap in shades and that type of thing. But these are things we have to deal with, right? Occlusions, right? I mentioned this earlier, where you might have a pedestrian that gets off a bus and then crosses, but that bus is blocking your sensors from being able to see that, hey, there's a pedestrian that's just about ready to walk out into your lane. It might be that we've all had the experience, if you drive, that you're maybe behind a big truck and you can't see what's going on in front of that truck. Okay, maybe you should follow farther behind that truck, but there's an occlusion going on there, right? So we talked about edge cases. Hybrid traffic ecosystems. I did mention earlier that, hey, this all gets easier when every vehicle out there is autonomous, right? And they can collaborate, and they can all use the same rules. There's a little game theory to explore there, whether some systems might try to game the game to try to optimize their performance versus the community's performance. But basically, things get easier when it's homogeneous instead of heterogeneous or a hybrid traffic ecosystem. But we got to deal with the hybrid system for a long time, right? Computation speed. So we talked about the dojo. We can also look at, I got 5 minutes. Okay, how much can I talk about in 5 minutes? We've got Tesla's hardware 4. Now, originally, Tesla used a board from NVIDIA and their Jetson Drive board, and then they developed a hardware 3, and now they've developed a hardware 4, and of course there'll be a 5, 6, 7, whatever, right? So, they're developing their own chips. And they've got all sorts of different sensors. The whole hardware 4 includes not just a processor board, but a certain set of cameras with certain set of performance and all. So there's some redundancy here. There's 2 chips. So one side of the board can fail, and we can still continue on. Excuse me. So this is really for the full self-driving package, which is the one that's going to get towards SCE level 4 and 5 faster than any of the other type of legacy hardwares, right? So not saying we're there, but that's what it's targeted for, is a full self-driving. So, yeah, they're so vertically integrated that because they're seeing this need for speed and scalability. Um, both data speed and data width, trying to combine both of those. Trust, explainability. I spelled that wrong apparently. So yeah, how do you get trust in these systems? In AI machine learning in general, there's this subdiscipline called explainable machine learning, where one of the problems with deep learning neural networks in particular is that we can't always predict or know exactly how something's learning. And kind of the um, some of the worst cases, bad cases of this is kind of learning racial biases and gender biases and that type of thing, and let's say loan underwriting or facial recognition issues and that type of thing, right? So, um, so we there's a subdiscipline that's focuses on explainability and all, so we can maybe get some insight on how a system is learning and whether we think that's appropriate or not. All right, fault tolerance, algorithmic, stopping conditions. When is it good enough? Economic issues. All right, so I'll mark that spot. We got through slide 31. There's another assignment up there. It's another little essay. This is probably a last essay, so don't freak out thinking this is an English course, literature course, or whatever, essay course. We'll get into more practical engineering type things, but yeah, kind of write up a little paragraph or a few paragraphs, a page, maybe 2 page. Kind of, you could do like a high level design document, like a proposal or something like that. Just maybe provide a block diagram of the system. I'd like you to pick something that's not like a Tesla or a robotaxi, right? Think of something different, right? So you can kind of use your own insights and stuff. So pick a domain, pick a specific type of vehicle in a specific domain. We've talked about a lot of those. I give you a few examples in here, and just kind of write that up. And yeah, give me a little bit of a idea there. Yeah, I kind of had that at 1 to 2 pages, but then instead of 1 to 3, but then I thought, well, you might put in a figure, a block diagram, a table, so might run up there. All right, run out of time. Everyone have a great week, and see you next week. Make appointments if you need some extra time, or visit my office hours next Wednesday. Take care.
Thank you. Thank you, Professor. Good day.
Professor, would I be able to schedule like just some time outside of the office hour, sometime tomorrow or Friday if you're available?
Yeah, hang on a second. Let me just stop the recording here. And